Everything we make, let's make a deal. Everything we make, we have to check. All right, I'll always make it, you'll always check it. Okay, you make it and I'll check it.
How can students make connections between the counting problems they do in elementary school and high school algebra? One key is Pascal's triangle, which is often included in the traditional high school algebra curriculum.
1, 6, 15, 20, 15, 6.
Oh, all right, now I see it. All right.
When the Kenilworth focus group students first approached the combinatorics problems, they often began by looking for patterns.
Well, once when we find one, we just do the opposite of it.
What do you mean the opposite?
Some of the patterns that emerged were finding opposites, pairing each tower with an identical tower with opposite colors.
When we found this one out,
Yeah.
we just put 2 blues on the top and 3 whites in the middle.
Oh, do they always have an opposite?
Yes. Yeah.
Another pattern is grouping,
Okay, so
grouping towers in subsets defined by the number of blocks of a chosen color.
Freeze group, just switch those around. Same thing.
In the Kenilworth study, the students went on to find a further pattern,
Weird luck.
that each time the number of possible blocks increases by 1, the number of possible towers doubles.
Well, it goes like in a pattern. You have the 2 times 2 equals to 4.
Oh.
So 4 times 2 equals to 8, and the 8 times 2 equals to 16.
I wonder why. If this is a pattern, what would you guess would be with towers of 5
If I had a guess,
by noting this pattern?
30, yeah, 32.
You would guess 32.
I would guess 32.
All of these patterns are represented in the array of numbers called Pascal's triangle. Blaise Pascal, a French mathematician, wrote about this symmetric triangle pattern in 1654 in the course of investigating probability problems. At the Ferris High School in Jersey City, New Jersey, a math teacher uses Pascal's triangle, along with combinations activities, to help her students grasp difficult concepts in algebra. Gina was a researcher in the Rutgers long-term study.
The more I have grown accustomed to listening to what students have to say and asking questions that will elicit their thinking, the more I've come to understand that the way I see something is very rarely the way that they see it.
Like a pattern.
Just like a pattern? Okay, and the same, you discovered something about these patterns?
Gina's Algebra 2 class is midway through a unit that includes Pascal's triangle and the binomial theorem. The binomial theorem describes how to multiply or expand an expression, such as a plus b, to any power. These expansions are frequently used in algebra, but they quickly become tedious if one has to multiply them out by hand. Pascal's triangle can provide a shortcut for finding the coefficients of the terms in binomial expansions. However, Gina introduces Pascal's triangle only after the students have experienced a number of counting activities, such as towers and pizzas.
Okay, tell me about towers. How does 2 to the n work with towers?
There's 2 different colors.
There's 2 different colors, and what's the n?
5. It could be 5, like 5 high.
Okay, so if it's 5 high and it's 2 different colors, then it's 2 to the 5th power? In the standard Algebra 2 curriculum that we follow, the binomial theorem is basically the end of the course. And it's something that we touch upon, and basically the students just expand a plus b to the 2nd, the 3rd, the 4th, the 5th, look for a pattern. Some students will have seen Pascal's triangle before, some students will have not. It depends on the class, but basically the idea is to get to the binomial theorem, talk about expanding binomials, and then you're done. That's the end of the year. Let's review. I think that the problems that we do, towers, pizzas, ice cream, I think that that helps to give them an intuitive understanding. And I think that the concrete objects and the other types of things that they've been working on, I think that gives them a really good basis for understanding why it is that this happens.